All right, in this video, we're going to talk about blood pressure, blood flow, blood velocity, resistance to flow, all kinds of stuff. Many of which were laid out in Poiseuille's law, right? The simplest version of which is shown in the upper right here. Q equals delta P over R. Well, let's point out what's in the graph first, and then we'll get to a few of these equations and what they're pointing out. Right, so at the very top here, we have a graphic showing the either vascular circuit. Now we've got the aorta here, so it's going to be systemic in this particular example, but it would look similar, at least in terms of anatomy, with regard to either pulmonary or systemic circuits. Now, of course, pressures and resistances and things like that are going to be different. Flow, though, would be the same, right? Because one circuit feeds the other, and so the flow of each circuit has to be the same. And we'll get back to that when we come back over here in just a second. Okay, so we have blood flow from our aorta into arteries, finally into arterioles, which we generally classify as resistance vessels, largely because they're so small, and they sort of represent the first major increase in resistance, and therefore a significant pressure drop, as you can see here, right? In this part of the graph, we have this big pressure drop at the arterioles. And then the venules, small veins to veins, and then back through the vena cava, again, in the systemic circuit. Now, if we look at blood pressure, we can see that blood pressure in the arteries is pulsatile, right? Shown by the waving line here, right? And that's why our clinically measured blood pressure is reported as a systolic over diastolic, right? It's two numbers, not one. And that's because it's varying with ejection from the ventricles. And of course, our pressure, we just said, is going to fall dramatically at our resistance vessels and then stay low throughout the rest of the vascular circuit before it comes back around to the heart. And of course, we could complete this circuit, if you'd like, where this would come back around, right, back into the heart to get repressurized and begin the circuit once again. Now, pressure, and I'll write it out over here for Poiseuille's law, Q equals delta P over R, right? And Q, of course, is flow, right? And so we look at our flow, right? We see that flow is actually pulsatile in the arteries, and then it becomes more consistent in the smaller vessels and then in the veins. And remember, veins are not small vessels, right? Small vessels meaning capillaries, and then they get big again. But what we can see is that if, going back over to our equation here, if pressure is pulsatile, it is directly proportional to flow. And so if pressure is going up and down, guess what? Flow is going up and down, right? And that's exactly what happens here. We get this pulsatile flow in the large arteries. Okay? Now, of course, when we lose that pulsatility, right, then, of course, our pulsatility of our flow also disappears as well. Now, going down another layer here, we have total cross-sectional area. And what we can see there is that the large vessels are very small in number, aorta being actually only one, and therefore have a very small total cross-sectional area compared to the small vessels, right? Capillaries and arterioles and venules, which in total have a very large cross-sectional area. And we'll come back to that in just a moment. Right? And again, because there are billions and billions of them, yes, they are individually tiny, but there are so many of them that their total cross-sectional area, if you add them all together, is actually significantly higher. And that's enormously important, as we'll see in just a moment, by looking at this trace, right? The blood velocity trace. And of course, high pressure is going to drive a high flow velocity. And of course, velocity is going to be pulsatile here as well because the pressure is pulsatile. And then, of course, we see this correlation where our large cross-sectional area results in a very low flow velocity. And that is absolutely essential, right? And the equation, first equation, maybe we should jump into over here, is that velocity is proportional to 1 over the total cross-sectional area, A, right? So our total cross-sectional area, as it goes up, right, we have more avenues for that blood to pass through that portion of the vascular circuit, right? Billions of capillaries through which that blood can pass with a much larger total cross-sectional area, right? Thousands of times higher than the total cross-sectional area of the aorta or the vena cava. And what that means is that flow velocity will fall dramatically, right? And that's actually very adaptive. And it's very adaptive because A, we want to get blood to the capillaries very rapidly. So this is very fast. And then we want slow, and maybe I should do this in a different color, right? Let's do this in green, right? Green for fast, green for go, right? And then we hit the capillaries, and because of such a large, right, inversely proportional to cross-sectional area, so this enormous cross-sectional area means velocity is very low. So we're going to be very slow through these little tiny vessels, and then we're going to come back over to larger vessels again, the large veins and the vena cava eventually, and we're going to end up being very quick again, very rapid, all right? And so it gets blood flow, the circuits essentially get blood flow to the capillaries very fast, where the blood flows more slowly, very slowly, and then very rapidly gets it back to the heart for repressurizing. And the adaptiveness of that is that A, we're moving oxygen as quickly as possible to the site of oxygen and nutrients and other things very quickly to the site where exchange can occur. Remember, the only place that exchange can occur is here, right? Only in capillary. Like the rest of your cardiovascular system exists for capillaries. The heart exists to generate pressure, to drive blood flow through the vessels. The arteries and arterioles exist to get blood to the capillaries. The venules and veins exist to get blood back from those capillaries. Highly adaptive, but remember the whole adaptive rationale is delivery and removal of substances from the tissues, and all of that exchange occurs through capillaries, right, across the walls of capillaries. And so we have this very slow flow rate across capillaries, allowing time for a very time-dependent process, diffusion, right? And so we need to have the blood moving as slow as possible, and still, let me give you this tidbit. Capillaries number in the billions, but they are all approximately 1 millimeter in length, right? A very small fraction of that in terms of diameter, but they're only a millimeter long. And it takes about a second, a little less than a second, for the blood to traverse that 1 millimeter. And that's enough time, it's actually a little bit more than enough time when you're at rest, for equilibration, right? For oxygen equilibration, carbon dioxide equilibration, glucose equilibration, whatever needs to move is going to move, have the time to move by diffusion. Okay? And then, of course, our cross-sectional area is, total cross-sectional area is going to fall, which means our velocity will rise, right, as we send blood back to the heart for repressurizing. Okay? So we've got lots of things going on here. So let's come back to Poiseuille's law for a moment, right? And one of the things I wanted to point out is that we talked about how this particular stacked trace here is for the systemic circuit, right? These blood pressures over here, right, are systemic blood pressures, 120 over 80 for a systolic over diastolic. It's important to note that cardiac output, left and right heart, in other words, Q for the whole system, right? Cardiac output would be flow for the whole system, Q is flow, has to be equal in the systemic and the pulmonary circuits, right? One circuit feeds the other, so we can't, if they weren't equal, there'd be blood backing up somewhere, okay? So in either case, though, delta P over R equals that same cardiac output, all right? Well, check it out. Systemic blood pressure is, mean at least, is about 10 times higher than pulmonary. So S for systemic, P for pulmonary, right? So systemic blood pressure, the mean pressure, is about 10 times higher than the mean pulmonary pressure. Okay, well, why don't we have 10 times as much flow in the systemic circuit then, right? We were talking about how pressure is proportional to flow, right? Well, that's true in a circuit, right? So we have this very high pressure giving us our cardiac output. We have a very low pressure in the pulmonary circuit giving us the same cardiac output. How is that possible? Well, it's possible because it's a ratio of the mean pressure, the delta P, the difference in pressure between inflow and outflow. I'm using mean pressure just because it's easier to talk about. But if we were to calculate a mean for either circuit, right, it's about 10 times higher pressure driving systemic blood than pulmonary blood. Well, the ratio has to be the same, right? If our cardiac output's 5 liters per minute, systemic versus pulmonary, and our systemic pressure is 10 times that of the pulmonary circuit, guess what? Our resistance has to be have a parallel difference between systemic and pulmonary, right? So in other words, we need a high pressure in the systemic circuit because we have a correspondingly higher resistance, right? And so in either case, this ratio, right, high number over high number equals low number over low number, right? Low pressure in the pulmonary circuit over a much lower vascular resistance. And in that fashion, we can end up with the same answer, same cardiac output for the systemic and pulmonary circuits. Everything else would look the same over here except for the pressures, right? The pressure would be significantly lower in the pulmonary circuit, right? Same is true of the cross-sectional areas of the vessels, and very similar, not the same necessarily, but very similar blood velocity, right? Because we've got to move this blood rapidly through the pulmonary circuit as well. Now, the pulmonary circuit is shorter, and so we need not have exactly the same blood velocity there. But regardless, we have two different scenarios for pressure and resistance in the two circuits that give us the same answer in terms of flow. Now, another thing I wanted to mention, talk about a little bit here, is our resistances, right? Because we talked about resistance of a vessel, right? So resistance in Purcell's law equals 8L eta over pi r to the fourth, right? And the 8 and the pi are constants because we're flowing through cylinders, and the length, L for the length and eta for viscosity, well, those are relatively constant. They tend not to change in a second to second. And so we can really simplify this pretty dramatically by saying resistance, and we shall say proportional to, is proportional to 1 over r to the fourth, right? Well, that's resistance of a given vessel. Do we have one vessel in this picture? Of course we don't, right? So Purcell's law, the resistance value within Purcell's law, when you're looking at an individual vessel, right, looks like this. However, when you look at a system of pipes, then we need to start talking about the total resistance of all of those individual pipes, right? And there are two types of resistances that we could assess here. We have what's called series resistance, and we have parallel resistance. Okay? Now, resistance is very hard to measure. It's almost impossible to measure for a complex system of pipes like this. But we want to be able to think about series versus parallel resistances. Okay? And in series resistance, it's really quite simple. Right? We'll use red for our vessels here. Right? So you have your aorta, and then that goes into, your femoral artery, and that goes into your anterior tibial artery, and so on and so forth, until we end up out here in these little tiny skinny vessels, right? Arteries. Or it doesn't matter, we can keep going into capillaries. And we can assess the resistance, right? Because resistance is based upon radius, right? That's its major factor affecting resistance. And that's because of friction, right? The surface area available for friction with the blood, right? But really, we would want to talk about resistance of this section versus resistance of that section and this section and this section, right? And then just add them all together, right? Figure out what the resistance of each of those individual pipes is, and then, right, you end up with this equation up here, right, where you just add them all together, okay? And of course, resist R4. Is R4 going to be the same as R1? Oh, heck no, right? Because the radius of R4 is tiny, right? So if that's tiny, right, its resistance is very high, right? And vice versa over here for R1, a large vessel. If the radius is very large, then the resistance of that particular segment is very low. Okay, so again, it's already like complicated, right? Because you got these vessels that are changing sizes as you go. And so our series resistance would be a very complex term. All right. And so you might think, all right, well, I can say most of the resistance would come from these little tiny pipes, right? And so, and I mean by a lot, by enormous factors, because the difference in diameter, we'd use radius, so cut these in half, but the difference is in diameter, right? Here's your aorta at 25 millimeters. And here's your capillary at 0.08 millimeters in diameter, right? Now, they're different by quite a bit, right? Now, put each of those to the 4th power, and it makes that difference enormous, right? A capillary has, approaching billion-fold differences in resistance from the aorta or the vena cava, right? And so let's put exclamation points out here for, this R4, right? These small vessels. So it sounds like all the resistance is coming from the little vessels, right? That's true to a degree. However, we have this parallel resistance thing, right? So in this case, RT in total, RT is total, right? So, and we'd have to have the combination of these two to figure out it, right? And I said it's really difficult to calculate resistance as a whole, but sounds like so far that we're kind of screwed by this R4, right? By these little tiny vessels. Like that's going to just be like the end of blood flow through these vessels, right? Because remember, flow is inversely proportional to resistance. And so these R4 here, this little tiny vessel has enormous resistance. What's its flow? Tiny, right? So it's like, the blood is flowing through the aorta and the arterioles, and it runs into this brick wall, right? When it gets to the capillaries where there is enormous resistance. However, look at parallel resistance, right? For parallel resistance, the total resistance equals the resistance of each, RE, divided by N, the number of vessels. All right. So now it sounds like the total resistance, like just think about just the capillaries for a second, remember? Because that's where most of our resistance is, right? In these little tiny vessels. But now check it out. The total resistance of all your capillaries is the resistance of one of them, resistance of each of them, right? One of them, divided by their total number. What did we just say about the total number of capillaries? Billions, right? Billions of capillaries, right? Thousands of kilometers of capillaries, and they're all only 1 millimeter in length. We are talking about billions and billions of capillaries. So plug in billions and billions, right? Plug in 10 to the 9th, right, for N. So even though the resistance is very high, look what we're going to do. We're going to divide it by a gigantic number, right? And if we divide a very large number by an even bigger number, guess what happens to our R total? It falls, right? And so that is how we accommodate having these little tiny vessels with huge individual resistances. We accommodate that by having billions of them, right? Otherwise, your heart would have to, be the size of a, BW bug, right? It would have to be huge and generate enormous pressures to drive through a single capillary. But we don't have a single capillary. We have billions of them, right? The analogy here is You driving on, 83 or 695, right? Driving on a highway, right? And there's an accident, right? If there's an accident and they close off 3 lanes of 695, what happens to flow? Aha, it drops dramatically. What happens when they open those 3 lanes up? Poof, right? All of a sudden flow is great, right? So there you have it. The more lanes, quote unquote, lanes you have, the lower the total resistance to flow will be. Now just think if, 695 had a billion lanes, you wouldn't even be able to find another car on the road, right? There'd be no resistance because there'd be so many options. Now, there's a lot of blood and a lot of blood cells, right? But you get the idea is that the more lanes we have, the lower the total resistance becomes. And so series resistance is bad, but it is balanced by parallel resistance that is reduced dramatically by the number of small vessels we have. Okay? Now, let's see. One other thing I was going to say there. What was it? Microvascular. I use microvascular rarefaction as an example of this. Microvascular rarefaction is a loss of microvessels. And it happens in response to, one of the things that happens in response to is high blood pressure. So think about this for a second. If you have high blood pressure, right? So delta, if we solve our Purcell's law for delta P, so delta P equals Q, which is cardiac output, right, times R. Okay? Now, if we lose blood vessels, right, if you're hypertensive, right, and you lose blood microvessels because of that, right, think about your parallel resistance. Your N is falling, which means your resistance is going up. And so if your resistance is going up, what happens to your blood pressure? It goes up, right? If your blood pressure goes up, your microvascular rarefaction gets worse and you lose more small vessels, which means your parallel resistance rises again and makes your blood pressure go up again, which makes you lose more vessels, which makes your blood pressure go up, which makes you lose more, right? So this is why hypertension is a vicious cycle. And so we have to usually step in and have interventions, pharmacological or otherwise, so that we make sure that we get that hypertension under control before it becomes this sort of vicious cycle of activity. And those small vessels will grow back with exercise and reduced blood pressure. So we can solve a lot of that problem, but we don't want it to become this vicious cycle. Right? Last thing I want to mention over here, getting buried in all the mess here, is compliance, which is C. Right? And compliance is really the give, and this is going to help explain our pulsatility of our pressure here. Right? So compliance equals, it's kind of like, I call it a measure of the quote-unquote give of a blood vessel. Right? And so it's the change in volume at a given change in pressure. And so if compliance is high, we get a large change in volume at a change in pressure. Right? So veins have high compliance because they quote unquote give easily. Right? If we put a lot more blood flow into the venous circuit, it accommodates it well. Right? Arteries have much lower compliance than veins because to get a particular change in volume, in other words, to get the vessels to distend, we need a much larger change in driving pressure. Now that low compliance is actually, there's another term for that. Low compliance means high elasticity. And that's actually a good thing in arteries, right? Because we need to maintain the pressure. We don't want the vessels to give so much that we don't get a large change in pressure, right? The more blood we can sort of squeeze into the arteries, the higher the pressure we can keep there. And to a degree, that's a good thing, right? Now, what it means in terms of this elasticity or low compliance is that as we push blood into those vessels, they tend to stretch and they tend to start to recoil, right? And so it keeps the systemic pressure, right, high, right, this pressure up here, high, because the vessel will not it will stretch some, but not a lot, right? Its compliance is low, so it doesn't give a lot, which keeps the pressure high. But not it would be higher if it didn't distend at all, right? But then watch this: when it starts to recoil, right? When we're not ejecting blood, the vessel will recoil, right? Which keeps the pressure higher, right? And so a little bit of distension at the top end keeps the pressure from going too high. Recoil at the bottom keeps the pressure from going too low. And so it reduces the pulse pressure of the vessel, this elasticity, right? The low compliance. And that's a good thing, right? Because we don't want, right? Remember we said this pulsatility generates this pulsatile flow down here. Well, right now, if our pressure looked like this instead, right? If our pressure, our vessels became non-compliant, right? Like they didn't give it all, right? And that actually happens with atherosclerosis or hardening of the arteries. Then they don't give it all. Then the pressure, systolic pressure rises really high, but then they don't recoil either, and diastolic falls really low. And so you get a pulse pressure that's much greater. And of course, that's bad for this pulsatile flow down here too, right? It doesn't go below zero, obviously, but you get the idea. Is your flow pulsatility goes up much higher. And remember, if it goes down here, right, that's flow of zero. You don't want no flow in between heartbeats. You want the flow to be consistent, right? You're going to get some pulsatility, but we want to minimize it through this elastance of the large arteries. You get over into the veins, right? We have much greater compliance, right? The delta V over delta P, right, comes much higher because a small change in pressure will distend those vessels dramatically, meaning we get a very large change in delta V, right? So large over small equals high compliance. And that actually allows us to keep the pressure in the veins very low, right? And that's actually really important for capillary exchange. We don't want back pressure in the capillaries. We definitely do not want high pressure in the capillaries. Remember that we said with hypertension, that's damaging, right? And so high venous pressure would be bad. And our high compliance helps oppose that. Okay, lots going on there, but good review of a lot of different things all in one place. See you next time.